and start recording today and jump all the way back to the beginning here. All right, so 2, 4, 6, 7, 8. All right, we're good. Let's see. I may also sit more and walk less today. Just, I don't know how, it's useful for me, but I don't know if it's all that useful for you all to see me wandering around. So let's jump into things. Hopefully everyone has, I saw that most people have done the homework. The simple, it's pretty straightforward. There were a couple of kind of quick questions on the homework. Has anyone not submitted the homework yet? The LMS Q&A, the simple assignment on there. Okay, I won't go into it then yet. I was going to talk about that. Maybe I'll talk about it next time. Make sure you get that out of the way today. It was supposed to be before class, but we're still learning our way around, and so I won't worry too much. What I like to do is give bonuses for stuff being handed in early, as opposed to major penalties for stuff being handled in a little bit late. Eventually, things are so late that I can't spend a lot of time catching up. But if things are just a little bit late, I'm not going to get too worried about that. But get that one out of the way. The other piece of today's homework was supposed to be getting the sandbox up and running on your computers. So hopefully you have Visual Studio up and running. You probably have had to build your own version of GLFW3, the actual kind of wrangling, or excuse me, not the wrangling library, but the sort of operating system abstraction layer for OpenGL. And we'll go into that. We'll kind of demonstrate that the second half of today. So if I can get through all the math stuff, then we'll get more into actually looking at the sandbox and why it's important and why we'll use it to demonstrate a lot of the stuff that you'll see in the lecture and throughout the class as well. So we'll go with that. And today I'm trying to keep my mask on the whole time, which is another new thing for me. So if I suddenly cut out, or you'll hear in person, you see me pass out, that's why. So, disclaimer, first off, even though this is a HASS elective course, which I'm sure most people taking a HASS elective course, perhaps other than some of the economics courses and whatnot, you might think, oh great, I'm doing this to escape math. And even though this is a HASS elective course, there's no escaping the need for understanding some of the underlying math when it comes to computer graphics. Hopefully, at this point in your careers, in your educational careers and your, academic, I guess same thing, careers, you've probably already encountered most of the core math that I'm going to talk about today, but you probably haven't applied it in the ways that I'm going to talk about today. All right, so the good news is we'll discuss that theory and work our way through some of the basic examples to illustrate, but in the end, it's going to be okay to use libraries for math functions. I'm not going to ask you to do a lot of, calculate by hand. Maybe we'll do a little bit of that with regards to the homework, and as we get into some fun things like quaternions, they're kind of a fun topic, and some basic kind of matrix multiplications and things. None of it should be that terrifying and frightening. So we're not going to do a lot of math proofs sort of thing. The important thing is to understand the implications of concepts and what they're going to, the implications of them running inside of OpenGL and being used for graphics, like the order of operations, the practices necessary to get the desired predicted results, right? So we have to know, okay, we do these type of operations in this order. That's a big thing. You do it in terms of translations versus rotations versus transformations, and that sort of thing. So we're going to be focusing on the what and the why of the math pieces, rather than on sort of the how part. All right, so if you want to go and find proofs and theorems and all that sort of stuff, there's whole books about the derivation of quaternions and imaginary, three-dimensional imaginary spaces and so on. It's interesting stuff. I encourage you to check it out if you like, but we're not going to get too deep into the woods on that. Now, that said, I also wanted to add yet another online resource for us, particularly because this one, I like the math in this one, the math pieces of these presentations, even more so, I think, than the other ones. So we had Learn OpenGL, we had OpenGL or OGL Dev. There was also, Scratch-a-Pixel. There's all sorts of great things. But OpenGL-tutorial.org, not quite as flashy as some of the other sites, but their math tutorials I find particularly good. They have two sections, one on matrices and one on quaternions. And you'll see I've used a couple of their pictures in the next two lectures you're going to see. I like them. So if you're ever in doubt on why something works a particular way, or you want to see some of the background information, you can certainly go to one of these sites or the other ones. We kind of pop around a little bit all over the place. If you're looking for a particular book, I can recommend some books. And as we get into some of the graphical algorithms outside of the 3D computer graphics, there'll be some other resources as well, right? We're going to be attacking things in a lot of different ways. And for now, we're still at the bootstrapping kind of phase. We want to get stuff up and running. We want to see it on the screen. We want to understand the basics so that we can eventually do things like draw lines for our own, even outside of OpenGL. Really, really kind of lower level primitive stuff. But in order to do that, we want to, deal with this chicken and egg situation where we want to get OpenGL running well enough so that we can see the results on the screen, because that's kind of cool, kind of important, right, to see that. So the foundations for today, we're going to be looking at coordinates and coordinate spaces, largely vectors and matrices, how they relate to one another. Just pull the door, it's open. Just pull it. There we go. For those of you online, so you get to witness this at some point in your lives. It'll be great. All right, now I'm going to sort of balance my ears here. Kind of trickier than I thought. Dangle this from my head. All right, so vectors and matrices, they're very related, very similar. One's more a special, sort of a special case of the other, and we'll talk about that. But in OpenGL and 3D computer graphics, they're going to be sort of our fundamental things we work with. Vectors are going to represent things like a position or a direction vector, and matrices are going to be our sort of fundamental thing for doing transformations, rotations, translations, kind of all moving stuff around the screen or transforming from one space to another space. Talk about that. So we'll mention those transformations and concatenations of transformations. How do we rotate and then rotate again, and translate and then rotate, and all those sorts of things. And we're going to have a very specific application of that with regards to the camera, right? So we want to talk a little bit about some foundations in terms of concepts of how we talk about 3D space and how we talk about presenting 3D and 2D and so on. Not many of us have a 3D display. So when we look at most of our graphics here, unless you have a VR device perhaps, and even then, you're probably rendering stuff on a 2D screen, even though it's 3D, right? So we have to do things like transform, translate, project 3D information into a 2D space in order that we can present it, right? So even if it's VR, it's two-dimensional displays, one for each eye. Rarely do we really present something in 3D. So most computer output devices these days are still 2D, but they use some special things about our binocular vision to make it look 3D, but we're not really using three-dimensional displays all that much just yet. So first off, three-dimensional coordinate systems. Pretty straightforward, right? We're all familiar with our wonderful friend René Descartes and Cartesian coordinate systems, X, Y, and Z. We have orthogonal axes that allow us to talk about these three dimensions, right? One thing we want to be clear on, though, is sometimes you have to figure out, okay, how are they oriented? And for that, we talk about being left-handed or right-handed, which basically means what direction is Z in with regards to X and Y. So by handed, we mean like, okay, if you took your hand and imagine your thumb is the Z dimension, and if you're looking at your right hand, you sweep your fingers from X to Y. We're always sweeping our fingers from X to Y, and Z is the direction our thumb winds up pointing in, right? So if we were left-handed, it would look like the one there on the left, where we would sweep X to Y, and we wind up pointing into the screen. Kind of have to really be awkward to perform that motion in getting it to point in the screen, but it's the idea, right? 3D coordinate systems, right-handed, left-handed. Why do I mention that? Well, sometimes in dealing with things like, DirectX, Direct 3D versus OpenGL versus, a particular game engine, one system might choose one or the other, right? So you do have to be aware. A lot of the concepts today, it's sort of like, you should be aware of this because the system you work in, and I hate to say, okay, this is the way to do it because it's OpenGL, because this, I don't want to give the impression that there's only one way of doing it, because there are, obviously, even Direct 3D and OpenGL do a lot of things differently. So it's kind of to be aware of that and for you to kind of consider these things as you look at them. All right. So congratulations. We've got to the point of thinking about 3D points that are often represented as a vector, right? We have an X, a Y, and a Z. And when we're working in graphics, usually we're working in something called we're working with something called homogeneous notation or homogeneous coordinates. So we have this extra coordinate here, we'll refer to sometimes as W, and quite often when we see it being used, we just see a 1 there. And for practical purposes, what does that mean? Well, in homogeneous coordinates, we have that extra term, and the real meaning of the vector, the real meaning of the values, is if we divided each of the others, the X, the Y, and the Z, by that W, that would give us their real values. So if we put 1 there, it's just sort of, we can kind of imagine, don't worry about it too much because everything divided by 1 is just itself. And so why are we worried about it? Why is it there in the first place? Well, you'll see as we get into the math that's involved, it's largely to make that math simpler and allow us to do kind of certain things as single operations and so on. Right? So it opens up a whole bunch of possibilities and optimizations and techniques that we can use for very, very little kind of cost. So usually we're talking about 4-dimensional vectors here, well, not 4-dimensional vectors, but they have 4 dimensions, X, Y, Z, and W that we'll be using. And most of the matrices that we're going to be using in 3D graphics should not surprisingly, therefore, be 4 by 4, because as we're doing matrix mathematics and we're doing matrices times vectors, we like to have things that match, right? 1 by 4 and 4 by 4, we can work with those. 1 by 4, 3 by 1, we can't work on that. So we have like non-complying situations there. So that's why you'll usually see 4 by 4 matrices and these vectors in homogeneous notation like that. Okay, so the W component is known as the homogeneous coordinate. To get the 3D vector from a homogeneous vector, we can divide X, Y, and Z by the W. Usually you don't notice because it's 1 most of the time. Advantages like matrix transformations. Without a W, we can't translate vectors. We'll talk about what that means. Right? Translation of vectors. Let's see an example of that in just a second. We also can use the W value to do things like creating 3D perspective. And this one, bold, that's a hint that we'll come and talk about this or important topic, important thing. Whenever the homogeneous coordinate is equal to 0, the vector is specifically known as a direction vector, right? Since a vector with a W coordinate of 0 cannot be translated. So we have this idea of direction vectors versus position vectors. So it gets us into a little bit of weeds as far as physics goes, when normally we think of a vector is a direction with a magnitude, as opposed to in here, well, sometimes we have this vectors in the vector matrix sort of way versus vectors in the physics sort of way, and can be a little bit confusing. But when we talk about points and we talk about direction vectors, we talk about kind of special cases of this set of 4 coordinates, where the w coordinate is either 1 for a point because it can be translated, or 0 for a vector because a directional vector, cannot be translated. It has no real position. It is just a direction, right? So direction vectors, w is 0. Position vectors or positions, w is 1 because we can translate them. Okay, so let's talk a bit more about vectors first. All right. So, like I said, a vector now in this sense, we're not talking about vectors just in terms of something that can contain multiple values, like a vector in C++. You might have also seen another confusing bit, right? We have yet another kind of vector. But in the simple case that we're talking about for the 3D math part of it here, we're going to talk about a direction. So, for example, you might have 2 points, and you might need a direction that points from one point to another point, right? So we can use a vector to represent the difference between 2 points. So if we had point 2 and point 1, P1, P2, and we wanted to figure out the vector between them, we could just subtract the 2, and then that becomes a vector that really has no position. I guess this is a slightly, it's always hard in here in terms of, it's hard to get the idea across that P3 here, yeah, it doesn't correspond to particular necessarily a location in space. If we just looked at it that way, it might, but it's really the difference between them, right? It's a matter of, you can add P3 to P1 to get P2, right? It's that difference between those two. So typically when we're talking about vectors, we're talking about a direction that gets us from one point to another point, but it can also get us from any point to some other point according to that direction, right? So we could really use that vector and add it to any point to get us to somewhere that was a consistent offset from that other point. So imagine we wanted to shift something around somewhere. We just add a vector and we just shift every point by in some direction, right? It would move it in some direction, right? Now, again, some of the background abstract math here. I'm assuming, and I can ask for actual show of hands, and people can actually show their hands these days. You should all kind of be familiar, I assume, with dot product, right? Right. Dot product of 2 vectors. It gives us, it's also known as the scalar product, right? We wind up with just a scalar value, which we want to look at the exciting way of it. We can use cosines and magnitudes and so on. But it turns out, for our purposes, there might even be some simpler ways. But it gives us a lot of time we use it to figure out, okay, some degree of similarity between vectors, how much of a certain component do they share in common so that they are similar or not. But we wind up with a scalar value that represents sort of a similarity. There's also dot products, also known as the similarity product there. The other one, of course, is the cross product. Again, show of hands, everyone should sort of be familiar with this. It's the idea, when you cross 2 vectors, you wind up with a vector that is sort of orthogonal to both of them, and it allows us to kind of figure out, okay, in graphics, we're going to use this for all sorts of things when we're trying to figure out, which way something is facing, or the direction, or the normal, things like that. Right, so it's going to be an important one. Right. So assume everyone kind of knows about them. So cross products is useful for finding out outward normal vectors. That's one of the fundamental things. We want to figure out, okay, once we have 2 sides of a triangle, that should be enough information as long as we know kind of which is which and our winding order, we can figure out, okay, does it face us, towards us, does it face away from us, that sort of thing. Right, so it's very useful for that. Now, we went through vectors real quick. I have to take my mask off for just a second. Behind over here, I think I have like a thread in my face or something. I feel like I'm getting something in me. Maybe I imagined that, who knows? Get used to that. Okay, back to So matrices. We'll introduce probably one of the simplest kind of matrices, other than maybe a null matrix, but the identity matrix, which is just a matrix with one along the diagonal like this. So this is going to be important because as we want to potentially, we'll talk about values changing or rotations, translations, and so on, we want to be able to kind of predictably apply things. And if we wind up multiplying things by an identity matrix, you should wind up hopefully getting, or multiplying a vector by the identity matrix, nothing should happen, right? That's the idea behind the identity matrix. Okay, if we rotate, translate, et cetera, by the identity matrix, nothing will happen. That's our first kind of setup. So why does that happen? If we have, imagine here we have an X column, a Y column, a Z column, and our W column. So the amount that the thing we're going to transform, if we scale X by 1 and add nothing of the others, if we scale Y by 1 and add nothing of the others, and so on, that means we should get the same thing back. All right, so I mentioned this about this multiplication, and this is what I mean by matrix multiplication. Again, also, show of hands, everyone done some matrix multiplication, right? So vector matrix multiplication, very similar to a dot product of columns and rows. A little example here at the bottom, dot product, right? And yes, I implied a little bit that vectors, I kind of been using, okay, matrix to matrix multiplication versus matrix and vector multiplication. Yeah, there's something to be said for considering vectors as being 1 by n or n by 1, potentially, matrices, right? As long as we're careful about how we work with them, we can kind of think of them in that way, and makes life sort of hopefully straightforward or intuitive, right? So pretty straightforward. Multiplying a vector or a point by a matrix. Now, one of the subtle things you'll notice in here is that we're saying, with the matrix on the left hand of the equation and the vector on the right hand part of the equation here. Now, I don't mean on the equals. I mean matrix here, vector here, right? Remember that for later. Now, in matrix multiplication, we just kind of go through the whole thing of it, all the rows, all the columns, as opposed to just having a single column. Pretty familiar. Some key properties of matrix multiplication, and one of the most important ones that we're going to think about here. So we've got commutative property, does not work in the case of matrix multiplication, right? You can't say A times B equals B times A. It does not. That's one of the biggest ones we have to consider ourselves in here and see what the results are. If you wind up in 3D where you're trying to rotate something, move something in a certain way, and it winds up being crazy, one of the first things you often consider is like, oh, did I get the order of operations wrong? Because it does matter, right? 1 plus 2 is the same thing as 2 plus 1, but in our case, matrix A times B is not the same as B times A. Pretty fundamental. Everything else should be pretty straightforward. Associative property, distributive property, these all hold true. And this bottom one, the dimension property, is an important one that you should also be familiar with. The product of an m by n matrix and an n by k matrix is an m by k matrix. Right, so some here. Not commutative. We can use the associative property if we want. Right? And the shape of matrix operations matters. One interesting thing is sometimes even things like OpenGL or some systems will say, oh, okay, you really meant to do this. And it might do some things which might defy some of the laws of reason and rules here so far. So it's best to be explicit and careful here, right? So in this class, for the most part, you're going to want to see, matrix times a vector equals a vector, right? So if you have a translation or a transformation matrix times a vector or times a point, times a, that we wind up with another point, right? So most of the time we're going to be moving points around, so we want to give it one point and come out with another point, right? So that's why this works, right? So this would be a 3 by 3 times a 3 by 1 gives us that 3 by 1 as a result, right? We're not going to do it the other way around, right? That's undefined. We can't deal with that. Now, if you want to insist on, say, having the vector on one side, well, I mean, when you get down to the fundamentals of the math piece of it, we certainly could say, well, instead of a 3 by 3 times a 3, times a 3 by 1 gives us a 3 by 1, we could say, well, what about a 1 by 3 times a 3 by 3 giving us a 1 by 3? Yeah, okay, that's legal, but we don't want to do that most of the time. It gets into this issue of whether we're performing post-multiplication. We're going to refer to these things as post-multiplication versus pre-multiplication. Kind of what side the vector is versus what side the matrix is. You're going to hear these terms, post-multiplication and pre-multiplication. If you do one versus the other, and your system doesn't know, or your particular library or your whatever abstraction layer you're using doesn't do it the right way, often there are ways you can kind of convert back and forth by doing inversions or pre-baking certain things in. And that is best avoided. Sometimes, as you get into hardware, it's unavoidable, and there's this term, or this issue that you can kind of run into that hopefully for the most part in this class we won't really have to concern ourselves with much or at all once we kind of get the gist of it, once we kind of work things out. It's a thing called column versus row major ordering. All right. When we're talking about matrices, columns and rows, that's easy enough. For rows and columns, or, well, okay, is it columns and rows or rows and columns? That's, I guess, as you start to get into your representations, that's potentially arbitrary, right? And that is something that the math libraries sort of have to deal with for us. And we'll see one kind of weird example of this in real life as we look at the sandbox today if we have time. And this row versus column orientation has largely to do with how things are laid out in memory and how the language that you're working with thinks things are laid out, right? If you say X, I'm going to draw this on the board here. If I say, and for those tuning in at home, I'm just saying X with square brackets, two sets of square brackets. The question is, okay, is it rows and columns or columns and rows? Now, why would you care about that? Why would you ever want to do one versus the other? And a lot of that has to do with hardware. In terms of things being laid out in memory in certain ways, for example, which is a deeper issue than we can really get into much today. But you can imagine if you have something in memory, if you have one thing that's next to another thing, all wonderfully conveniently located side by side, accessing them is generally more efficient than sprinkling them throughout memory in some kind of way, having big gaps between them. So sometimes someone will implement a math library in such a way to take advantage of those things or take advantage of certain operations of the CPU and so on and so forth, and that will have an impact on whether they want to be sort of row major or column major. So it's sort of a hardware issue, or mostly a hardware issue, sort of, but no, it just sort of has to do with how things are laid out in memory. The good thing, generally, once we get into, and especially because we could use a math library again, we can kind of deal with this. We need to make sure that the math library that we're using, in this case we're going to use GLM, which is great because it's meant for using with OpenGL. And so it accommodates OpenGL and vice versa. So everything is going to be pretty straightforward. But if you go from this course and you try to do, implement something say, that you saw here and you try to do it in DirectX, you may have to figure it out. Don't try to use GLM with DirectX. And this is kind of one of the reasons why, just because this kind of thing that they don't necessarily agree on. And then there's lots and lots of discussions. It's a confusing thing. It takes a while to kind of deal with it, to really get a handle on it. But it's something just to be aware of. And it's just all this issue of sort of how things are implemented and laid out in memory. Are the columns clustered together, rows clustered together, so on and so on. Hopefully you won't have to deal with it much. If you encounter it, you'll at least know what it is. So we have all the basics covered now in terms of the math, right? The abstract principles. We have matrix multiplication, matrix vector multiplication, why we want to make sure 3 by 3 times 3 by 1s, and so on and so forth. So let's talk about what we're going to do with them, why they're so useful. So it's all about transformations. So what we want to do is basically take a point and move that point according to some transformation, right? A transformation is to say, okay, you have one point, you transform it, it becomes another point according to some fairly straightforward or useful geometric transformation, a rotation or translation or scaling. Right? Those are the three types of transformations that we're going to talk about. So the first one is the most simple, the translation. And for that we have a translation matrix. And it's a lot like adding an offset. We talked about just having a vector, and you sort of want to just add that vector to every point. So imagine we had a model, a 3D model that's made up of lots of vertices, and we want to just shift that model somewhere around in space. Right, so we want to just offset it somewhere. We don't want to rotate it around the axes or make it bigger, smaller, or anything. We just want to shift it around. So for that, we want to do a pure translation. Now, this is the first point at which, whether we choose to be post-multiplication, pre-multiplication, column versus row oriented, this has become sort of the standard notation, the standard way of looking at it in most modern graphics books, and this will let you know if someone's thinking OpenGL versus DirectX and so on. You'll see here this matrix, which sort of looks like the identity matrix there, but it has these new terms, tx, ty, tz. And they're in that last column there. And because I have my vector over there on the right side, x, y, z, and 1 as my w, if I go ahead and just multiply those, take the dot product, for each one, I say, oh, x times 1 gives me 0, y times 0 equals 0. I'm just doing across the top column using the position there. So 1 times x gives me x, y times 0 gives me 0, z times 0 gives me 0, tx times 1 gives me tx. So I add x plus tx, and that is now a translation in x. I've moved it somewhere. I just added an offset to my original value. So do the same for y and ty, z and tz, and so on. So I went with a simple translation. Things kind of just moved. I added something to each of the components. Piece of cake. Now, you'll notice I did an addition. I've translated there. It sounds like I added an offset, but I actually accomplished it using a multiplication. All right, I multiplied this vector times this matrix. So all of our transformations are going to be the result of multiplications. Even when we want to add transformations together, we're going to do multiplications. So we're going to combine things through these multiplications. It's all about multiplication. So in GLM, like I said, we're going to abstract this a little bit, and you're going to see, okay, we create a translation matrix using this pretty straightforward syntax here, GLM, :translate, and you give it the x and y, z values you want to use. That will give you a translation matrix, and then you just multiply that times the vector that you want to translate. Pretty straightforward. Next up, scaling. So in the case of scaling, we want to, scale something up. We want to scale it up, make it bigger, scale it down, make it smaller. Again, we're not going to do any sort of rotation. It's not going to move. Well, the points will kind of move, but they'll move proportional to their original value. They're not moving by an offset. And so for that now, we just have a scaling factor for each of them for a straight scale. Now this is going to be this could potentially be a non-uniform scale. If there's a scaling value for x, y, and z, if you wanted to uniformly scale something, they would probably be all the same. If you wanted to say shrink something by half, you would say 0.5, 0.5, 0.5, which actually be shrinking something by down to an eighth of its size, because we're talking about volume versus just a scalar here. But anyway, so if we wanted to make something sort of twice as big in every dimension, we would have a 2 there. If we want to make it half as big in every dimension, we'd have 0.5 there. And you can, the math, again, pretty straightforward. X times whatever the scaling value of x is, and then y times 0, z times 0, w times 0, and so on. Right? So even w is going to get scaled, but w is going to get scaled by 1, so it all works out nicely. Again, pretty straightforward. Oops. Now, along comes the 1700s. Suddenly it became history, a history lesson. The mathematician Leonhard Euler, I guess it's Euler, showed that a rotation around a desired axis could be showed instead as a combination of rotations around the x, the y, and z axes. Right? So normally you might think, okay, I want to rotate on z, that would be an operation. I want to rotate on x, that'd be an operation. I rotate on y, that'd be an operation. But instead, Euler came along and said, yeah, you know what? You can actually combine these rotations, and as a result, we now have, of course, the Euler angles that we have, grown to know and love. And sometimes it's easy to deal with, and sometimes that's the thing we want to present to users. If you've ever, worked in Unity or most other 3D engines, is a simple X rotation, Y rotation, Z rotation behind the covers. It just does it for you. Things just happen automatically. Now, there are bunches of problems, however, with using Euler angles, and specifically, if we didn't have to worry about them, if we only use the engine, we may never see it. We might never worry about it. But here we're not talking about an engine. But for compatibility's sake, there are ways to work with Euler angles, and you'll notice. Normally, when you want to create a transformation matrix that we can use to rotate something x, y, and z, you'll see it's Euler angle y, x, z, and that's not a typo. That's because one of the weird things we have to do is we have to say, well, if we have these 3 distinct rotations around that axis, what order do we apply them in? So the standard has been y, then x, then z. It kind of seems odd and arbitrary, and it is. It's sort of like, well, okay, that's the way it winds up. The problem is you have 3 axes, and you're not really, if you are thinking about them like that, you kind of think, okay, I rotate this much, then I rotate this much, then I rotate this much. Sure, you can have an operation that represents that, but your assumptions have to be sort of baked in terms of where you rotated things. It's not really a pure rotation. It's a combination of 3 rotations, which is so-so for a bunch of reasons. But you can do it, right? So if we want to create a rotation matrix and rotate x by theta degrees, we have this first case, y by theta degrees, second, z by theta degrees, and so on. And then you can combine them, but you have to decide, okay, what order do you want to combine them in? Now, other than strictly just worrying about that order, there's also a bunch of problems, potential pitfalls working with Euler angles. Right? Interpolating, you might say, well, why do I care about interpolating? We're always talking about interpolating for some crazy reason. But interpolating smoothly between 2 orientations turns out to be difficult. Right? If you just have those, interpolating between matrices is not really necessarily a straightforward thing. It also can it can often wind up with kind of very odd, kind of lurchy behaviors and so on that aren't just nice and smooth. Applying several rotations in order is complicated and imprecise. You have to compute the final rotation matrix and guess the Euler angles from the matrix if you want to kind of work your way backwards, because there are lots of different versions of the matrix that will kind of give you the same version of that combination of Euler angles, which sort of hints at this next one here, this well-known problem called gimbal lock. So gimbal lock, sometimes, depending on the orientation or the alignment of certain rotations that you may perform, they'll wind up blocking certain rotations and create other singularities which will cause the model to sort of flip upside down in certain circumstances. So if you look at our little animated image here, you can see as certain axes align with one another, like in this case now the ship is just sort of spinning, and it'll spin no matter if I spin the innermost or the outermost axes, once the middle axis sort of collapses into either one of them. Right, so you have these weird situations where if you've done a rotation and it may cause the collapse of a set of angles or set of axes, and then you can't actually get the rotation that you want to. Right? It's a mess. It's just basically a mess. You have to have the right order, but you might use a library with a different order for some crazy reason. All sorts of different things about it. And some operations are also going to be particularly complicated. Rotate n degrees around a specific axis, you're going to have a specific case, and so on. And did I mention, of course, gimbal lock, right? That's one of the biggest ones. We always love to point that one out as being a problem. Whew, talking so much with the mask on. If I sound awkward, it's like every so often, like, all right. So in graphics, we prefer to abstract rotations if we can, just a bit. And often we want to do all of our rotations in a single step so that we can make sure the assumptions are correct. So GLM, our math library, will have a rotate function. It has a rotate function that allows us to say, okay, rotate this matrix according to an angle and this x, y, and z. So what this means is we don't have a rotation for each of x, y, and z. What we actually have is a description of an axis which has some x, y, and z value. And then we have an angle that tells us how much to rotate around that. So it's a different representation itself of a rotation because it has a specific operation. It is orderless, right? We don't have to do things in a particular order. So under the covers, this helps us to avoid things like gimbal lock using something called axis angle, or specifically quaternions for our rotation. And this is that other OpenGL tutorial site. It has a pretty good explanation of the quaternions, and I borrowed a little bit of their stuff in here. So the idea behind quaternions is a long one, right? Going into quaternions themselves. Right? This idea, fundamental idea, is that you have a axis, which can be, imagine a direction vector somewhere in space. It points, it just has some orientation somewhere, a direction, and we're going to rotate around that axis, right? That should be pretty straightforward, right? Imagine, in the case of, if you said, okay, this is the z-axis and rotate around the z-axis, that makes perfect sense, and we can certainly represent that same way. It's sort of a simple case of an axis angle, right? It would be just the z-axis and some rotation around there. But this one, we can say, okay, along any axis, some rotation. Now, a quaternion is therefore, it's a set of four numbers, or an axis angle rotation is also a set of four numbers representing, now this is specific to quaternions. This is a good thing to refer back to. In the case of a pure axis angle, we would just say, okay, here's the axis, here's the number of degrees. We use quaternions because they make math even a little bit simpler. So most of the time, I've yet to see anyone actually doing, once you're in Unity, you work with, or Unreal, you're aware of quaternions, but usually you're just like, okay, I'm going to use them for my operations and not have to convert back and forth. But here's the way you can actually do it. And here's what they really represent. Quaternions aren't just the normal XYZ of the axis and the angle. It actually stores the half cosine, or excuse me, the cosine of the half angle as W, and then scales the X, Y, and Z by sine of the half angle. Right? That just winds up making certain operations, so there are other operations kind of more straightforward and subject to better optimization, streamlining things. Right? But fundamentally, it all has its basis in this idea of an axis and an angle. And the cool thing is then, you can imagine if you want to interpolate between them, it's a lot more straightforward because you can imagine, okay, here's the direction I want to interpolate, that's going to give me somewhere in between. And the amount of rotation, okay, that's somewhere in between. It's not quite normal interpolation. We have this thing called spherical linear interpolation in this case because it's a little bit fancier. But it does allow interpolation to be a lot more predictable, precise, smooth, fluid, and so on. Here's just a reference. So yeah, all right, you might look at this matrix and say, or this operation and say, well, that looks awful, but it's pretty straightforward. If you have the values of your quaternion, you want to turn that into a multiplication matrix because, well, when you actually do the transformation, we like things being as matrix transformations. So this is converting a quaternion to a typical transformation matrix. Right? There's a bunch of references out there if you want to see the whole derivation step by step. That's available, but we're going to reserve that for now, or else we'll never get pixels on the screen. And again, of course, the good news is that in GLM, you have this simple way to convert a quaternion to a matrix. Does it for you. So now, let's step back. So now we have these transformation matrices that allow us to do things like rotate something in space, so rotate it around an axis. So if you had, a picture of a spaceship or a monkey, and I forget the monkey's name offhand. Does anyone know the name of the monkey? It has a name. It's like Luna or something like that. Wow, I can't believe I forget the name. So we're imagining, okay, a translation is just moving our monkey's head somewhere in space. Our rotation would be rotating it around some axis. If we wanted something circling around the sun, that's a rotation, right? Or, depending on what it's rotating around, it could be rotating around its own center. So it could be doing like the Earth, spinning on its own axis. The question is, where is the axis that you're rotating around? Is it your own axis? Is it the solar system's axis, the sun's axis, and so on? And then potentially we have this idea we can scale it. So we can scale our monkey head up and down, so on. Now, what do we use those for? Why do we care about those things? What's the usefulness to them? And well, the basic thing is the idea that you want to be able to put things into the world, into this world that we want to ultimately render, that we want to show. So we start off with a model that maybe is created in some application like Blender or anything, some application, or maybe even specified it by hand. You said, okay, here's all the vertices of this model. You model the cube, you use it all, unit dimensions of a cube and so on. And you say, okay, I want to put it somewhere in the world. So you have these sort of two spaces, these two coordinate spaces, one in which the model was created, and the other one being the world, and where you want the model to be in the world. The center of the cube in the model space, that might be the origin of the cube. Might be. And then you put that cube in the world somewhere, you have to shift its orientation, its coordinate system, according to some position that you want it for in the world, position and orientation that you want it to be in the world. So how do you go from one to the other? How do you go from this local model space to the world space, right? The dimensions and orientation of the simulated scene being built. So you say, okay, this cube is at this place. It's part of a wall, and we want to create a wall of all kinds of cubes. Each cube is going to have its own position and orientation in the world, just like every object in our world has its own. So we have a matrix that we're going to refer to as the model matrix. And this is going to allow us to uniquely position a model in the world. So it's going to be a transformation that we apply to every vertex belonging to that model. That's going to put it somewhere in the world. Right? Like I said earlier on, imagine I had this object and I'm going to move it somewhere or slide it around the world. I would just have that translation, that offset, and I could position it in the world that way. Right? And then if I want to rotate it, and so on and so on. Right? So that's how we're putting things in there. So we have a model matrix, and we're going to refer to that as M, capital M. Right? So imagine this, I don't know how well we can see this. Maybe if I turn this light off. See a little bit better. Yeah. So you can see on the left-hand side, we have the origin at the center, more or less, of our monkey's head there. And all of the vertices in there are defined explicitly, and that each of them has their coordinate in model space, right? We don't describe them as a transformation of each and every point in model space. They just have a coordinate in model space, for starters. And then we use the model matrix to say, okay, shift this whole model from the origin of the world to its position in space. All right? So that's the model matrix. Starts off in its space, transforms into some location in the world. So that makes perfect sense. We have things in the world. Now, in graphics, though, that's not good enough. Just knowing something is out there is one thing, but there's this ever-present notion that we want to look at things. There's some idea of an eye or a camera or the thing that is determining what you see in graphics, right? Graphics is all about it. We don't just create a 3D world. Sooner or later, we want to be able to see it. We want to be able to render it. We want to create it, present it on a screen. So we have the other piece of the equation, the other party in this interaction here, the camera or the view, the eye. So the world space as seen from the simulated camera or eye, right? We have, imagine, just like we put the monkey's head somewhere in space, we want to put the camera somewhere in space, the eye somewhere in space, and have it face a certain direction. So it has an orientation, so it has a rotation, has a translation. Potentially, does it have a scale? Well, yeah, okay. Has a zoom, right? Depending on where it is, things may seem larger or smaller, right? And ultimately, what the camera sees is we render things out. We wind up with this thing called the projection plane, which is hopefully going to collapse what we can see onto a 2D plane that we can present to the user, right? So you see we have objects in the world on the left side. You might have other objects in the world that the eye cannot see, and they wind up being left out. And anything that the eye can see, it winds up being projected onto this projection plane somehow. So in OpenGL, in the old days, there was this notion of having a fixed camera, and you would just say, okay, you have a X and a Y and a Z offset, for example. So therefore, we would say, all right, now we have the camera's orientation or the view's orientation, and we have the model's orientation in the world. So how do we combine them? How do we get the camera to see the model or not see the model? It's going to depend. So we just work it out, right? We're going to transform things between the two. They have that relationship. So in math and combining rotations, combining transformations, we like to do this multiplication. So we could theoretically just say, well, okay, I have a model matrix a model transformation and a view transformation. I just multiply them together and then transform all my points according to the result of that. So a point in its own model space winds up being translated into camera space by multiplying it by this combined model view matrix. Sort of looks like this. Right, so this is our view matrix, which looks a little bit fancy, a little bit different. It has its camera rotation values, but we'll use the negative of the camera rotation angles, and we use the negative of the camera location to create this viewing transformation. Right? So that gives us the camera or the view matrix. So we combine this view and the model transformations by multiplication or concatenation there. But let's think about this for a moment. What are the implications of that? Right? We have the camera, we have the model. We did this weird thing where we combined their transformations to get the result. So the question is, okay, we're always transforming the points, but I said I moved the camera. But I didn't actually move the camera because I actually moved the points. So what does that mean? We have this negative camera rotation and position. Wait, what? Why? What does that mean? Well, let's see if this. Well, don't tell me this is going to work. All right. You know what? Okay, I've got to get this to work now, because this is no fun. It loses all the impact of that sound. So let's see if I can get sound here. I promise there won't be too many pop culture references, but hopefully there'll be fun ones. And let's see how loud this is going to be. Oh, it's not going to work? Boy, that's not working. That's so super anticlimactic. And it's probably broken other things. But you'll have to look this up. If you look up Planets Express, those who are following along at home, you can just click the link. So I don't know why our speakers aren't just working. There's probably something I have to change 5 ways. There's this epiphany in how many are familiar with Futurama? It's great, now it's a bit dated, I guess. But there's this epiphany in there when they're talking about the way that the ship works. They're all in a spaceship there. And this epiphany is that, well, the spaceship itself does not actually move. When they try to travel somewhere, they don't move the ship. What they do is they move the entire universe around the ship. Right? Everything moves around the ship. So if you want to get somewhere, okay, you just have to change the location of the place you want to move, as opposed to changing the position of the ship. And that's really what's happening with the camera in these cases here. Right? The camera is not really moving. We're transforming the objects in the world opposite the camera. That's where we use the negative rotation matrix and the negative offsets and so on. Right? Because we're allowing the camera to be still and just move everything else around the camera. Kind of crazy, right? I mean, this kind of, I see a few people scratching their heads, so okay, hopefully it's, sometimes I like to point out, or I'm hoping I'm pointing out something that seems like an odd thing, and if everyone else is like, it's all simple, and I was like, oh, well, maybe it's just me that thought it was odd, but it's kind of that way. Now, we can go one step further, and unfortunately my next pop reference, and I have to have a matrix reference, and I invite you to also the famous scene. Who hasn't seen it? Everybody seen The Matrix? Right? The famous scene, there is no spoon, right? And the next big epiphany in OpenGL is there is no such thing. There is no real camera. right? Especially in programmable pipeline OpenGL, there is no camera. Right? All you're doing is you're changing how things are presented, you're changing how things are shaded, you are modifying, effectively modifying those objects in sort of this space that ultimately sort of is there. There is no real camera. There's just another transformation. And this one's the transformation that the camera that we need. We kind of bake certain things into them, and we like to think about it in certain ways that allow us to like think that there's a spoon there, so we can deal with it as if it were a spoon. But fundamentally, it really isn't there. Now, one of the things that we have to do, that special transformation allows us to do, that gives us this camera-like perspective, is we want to deal with perspective. And the idea behind perspective, you've probably heard at some point in your lives this notion of a vanishing point. Right? So because of the way we deal with everything, square things in the world, or the way we perceive things, we don't really, things are square, but often, with distance, things look smaller, right? It's actually a pretty good, it doesn't mean to be a perspective drawing back there, but actually the illustration of this room where all of the cabling comes to the center point is kind of pretty cool perspective drawing. Right? So small objects, or the same size object in perspective will seem smaller in the distance. Right? Parallel lines will converge as they move off in the distance. Right? This concept isn't a new one, but it was sort of a breakthrough one in the world of art. Wasn't always there, even though it seems like an obvious thing. But back in the 15th century, here's one of the great examples of perspective being used. And that's what allows us to see things as 3D, right? Because that's how we experience them in the real world. That's how we know that depth, where that distance comes from. The impact of distance on the size of objects gives us those cues about how far things are apart, the depth of the scene, as opposed to just the X and the Y. It gives us those cues about that value. So we're going to think about some special things with this perspective view and how it's defined, this perspective or projective transformation that we're going to use to kind of give us the impact of the real-world camera. So we're going to think of this thing, this concept called the viewing volume, or the frustum. So the viewing volume is basically the things in the world that you should be able to see. You should be able to see things that are within that viewing volume in the world as defined by the camera and some parameters, right? The eye and some parameters. So imagine now we have a simple scene here. It has just a cube in it there, a box. And we have the eye over here on one side. And a few things about that. We have the obvious, the distance from the eye of where the cube is and so on. But we've got a few other constructs here. We have this thing called the near clipping plane and the far clipping plane to define that volume. Now, that's becoming less and less obvious in computer graphics and games these days. Used to be much more an issue where you'd say, okay, things over in the distance, I didn't want to render things that were so far away that they didn't matter, I couldn't see them, or they became trivial. So we would clip things that were further away than a certain distance, and potentially things might be so close to the viewer that they would overwhelm the scene, so you'd have this near clipping distance. You only were really interested in presenting things between these two planes, this near clipping plane and a far clipping plane. And if you have Unity on your computer, you can check there for the camera, you can define those things, the near clipping plane, the far clipping plane, for those purposes. So those are two important things. But then, how do you define the size of those things? It's not a volume. We just have two planes, and that doesn't give us anything but the volume that's in between them. It just gives us, the potentially infinite space in between two planes. Goes off in those, you know. So we have another variable here called the field of view, which is going to establish the angle. Normally, we talk about the y, so how tall, or in terms of degrees, how wide our field of view is, and that'll ultimately give us a width and a height potentially for that clipping plane, that near clipping plane. So we have a distance from there. Distance from there are z near, z far. We have our field of view, and that allows us to create a projection matrix. Turns out it's not all that difficult once we have those values. So we have the field of view, the z near, z far, and everything just works. But there's this one other number in there, this thing called aspect ratio. And before HDTV came in, and we all said, oh, is this 16 by 9? Is it 4 by 3? Is it now? It's talking about aspect ratios is much more common than it used to be. But when you hear, we're discussing monitors and things, we say, oh, 16 by 9, it means, okay, what's the ratio of the width of the monitor to the height of the monitor? TVs, televisions, most monitors used to be 4 by 3, something close to square, but not actually square. But now, most monitors have this 16 by 9, or even 21 by 9, 32 by 9. There's some really, really crazy wide displays and so on. So we need that to factor in here. Why? Because it gives us this sense of the relationship between x and y, the width and height. And the reasons for that is because this thing, normalized coordinates, normalized device coordinates, which in the world here, there is no difference between x and y, right? Locations are square, pixels are square in an abstract sense. But as we stretch and scale and so on, our viewing port, if we ignore that, we continue using these normalized coordinates, we wind up potentially stretching and squashing the object that we're trying to present, because like I said, there is no real camera that we're just moving around. We're affecting what's there. So even when we just change something about the view like that, we have to account for that. If you have, assuming now everyone has loaded the sandbox and you wind up getting a square, you might have noticed when you dragged it, or you increased the size, the textured, or even the triangle, everything kind of stretched or squashed. And that's because it has no concept. It actually is using no perspective matrix at all, no projective matrix at all, no transformation. And therefore, it does wind up doing these odd things. It just kind of seems weird and flat. Yeah? Why is the negative one there? Because you wind up with, in order to let me see. It just seems so out of place. Like everything has a reason. That's in the Z column, right? Yes. Trying to think. No, my other version of this, I went into the whole depth on things. Let me get back to you with a couple of slides that kind of go through the derivation. It's not exactly off the top of my head. I need more oxygen going to my brain for that question than this mask is allowing me. So that's a good question. I'll come back to that one. All right. So that whole process, it isn't quite as obvious as we'd like it to be. And ultimately, that matrix is a bit hard to read. So, yeah. So it does generate a kind of hard to read matrix that is sort of normal, kind of standard 4x4 matrix, sort of, kind of. But we wind up doing things that there's enough in there, and there's enough kind of odd things that go on is that so that there is a GLM function specifically to create our perspective matrix for us, or perspective transformation for us. It's another one of those things where we want to be a little bit removed from the math if we can be. And perspective is going to try to bake in the basics of that, which is our field of view, our aspect ratio, our near clipping plane, and our far clipping plane. Right. So it'll wind up baking that in. And one of the things about why that looks as odd as it is remember this is we have clipping as part of this, which clipping wasn't one of our sort of normal transformations where we said, okay, things are either in the scene or not in the scene. So what happens is ultimately that's going to kind of be part of how we can have things that transform themselves out of the scene entirely based on clipping. So that's why it's not quite exactly normal, straightforward as it was. So we'll get more on that at a later date. So ultimately, sometimes you might want to build a single model view projection matrix, and you can do that. And ultimately, the point winds up in its own, well, starting off in its own model space, can then be transformed to its final perspective orientation in one step by just doing a multiplication. Right? You can combine the projection matrix along with the model and view to get that MVP matrix. Right? One thing to be aware of, if you've keenly been following along, is notice it is multiplied PVM, but we refer to it as the MVP matrix because we do them in the opposite order. Right? So be aware of that. It's going to be interesting. We talk about them, just you can bake them in. Who does that operation? Where is it? A lot, we're going to get into the practical applications and where we do that tomorrow. So this is the putting it all together part, right? We start off in a local space, and we have a set of points. We transform a model by its model transformation to put it in world space. We then use the view to get it into view space. And ultimately, you have this projection matrix to get it into the clip space. Right? Some of this we like to abstract a little bit in terms of what the actual screen versus clip space can do for you. So some of it is still abstracted just a little bit. So here's a bonus if you want to, and this could be a added exercise, bonus exercise in creating what's called a look-at matrix, and GLM will provide you a way to automatically do this as well. But if you want to do this as an exercise, it could be part of a project, for example, to implement a camera that uses a look-at matrix, which, given the orientation of something in space and the position of something in space, if you want to have the camera always oriented and looking at that object in space, you can create a special matrix to do that based on that relationship between the eye and the target and certain orientations. Right, so that's a fun extra piece. All right, so that's actually, we made better time than I thought I was going to. All right. Any questions? Stopped along the way for more questions. So let's see. Let's jump over then to some other things, and this will just be a bit more, well, you know what? We'll continue to sort of barrel through, I guess, a little bit. Let me show you one little bit of things. So this is a slightly modified version of the sandbox again. Now this is the more advanced, using the main.cpp portion. And I've gone so far in here as to actually add a set of transformations here, or at least there's one sort of hidden transformation and one overt transformation. There's a set of numbers here. And let me try to this. And you'll see, as I was mentioning here, there's no perspective or projective matrix in here. So as I change the size of the window, because that square is, it thinks it's just 1 by 1, and it doesn't know anything, just keeping those spaces, and the space on the screen doesn't have anything to translate between the two. That's why it stretches like that. So down here, I've used IMGUI, and this isn't in your version. We'll have, I think, most everything up here, but not this matrix at the bottom. And I'm going to encourage you to dive into IMGUI a bit as we go, and I'll provide examples of it. So I don't have, actually, do I have specifically? I guess I should create more of a more tutorial run-through for IMGUI a bit. It's designed to be simply used. That's always like the conundrum, right? Something is designed to be simply used. How much should we cover it? But in this case, this kind of looks like our identity matrix. If I said, okay, 0, 0, I'm going to put 0 there, 0 there. And this matrix down here, I can refer to transform in this shader. Oh, that's not the one. That's the hidden one. I should use the other one. All right, I said use that, nothing changed. And that's because I'm transforming by the identity matrix. Right? And say I wanted to scale my x value. Scale it by 10. Too big. Obviously 0 is too small. 9,000. I want it to be 0.9. So there's it scaling x by 0.1, so the x is 1/10. And you can imagine as I was going along there, at some point I kind of hit it was like almost square again, because I sort of scaled the x in an appropriate way to overcome that weird aspect ratio. So let's set that back to 1. And I'm not going to try to do the rotations by hand. I'm not good within my head trying to do. This would be one of the homeworks, to put some of this to be a quaternion or an axis angle, and do your rotations around that. Right? That'll be one you'll get into. But this is the caveat, the weird thing. The matrix there is actually just looking at it in memory, kind of different rows of memory or contiguous floats in memory, and showing them out in the order that they are in memory. So the weird thing is, normally, you'll notice in the lecture, this rightmost column is where normally we would think of our rotations, or excuse me, our translations being in this column over there, tx, ty, tz, times our point over there. But because of the way that memory really lays out, I put them by hand. I have to do my translations here. The whole thing is actually inverted because of the memory layout. So there I'm shifting by x, which in our lecture notes and in most textbooks you'd see it up here. That would be x. So here, imagine you sort of, where you can think of it 6 ways one way or half dozen ways another. It's like, oh, okay, I'll just do this, but I'll think of it as pre-multiplication instead of post-multiplication. So imagine my x, y, z was over here, now I'm talking about a 3 by 1 instead of a 1 by 3, and the end result is going to be the same, but I'm going to just interpret it that way. It kind of works out. Whereas, okay, here's the 1 XYZ 1 as opposed to XYZ 1. At the end of the day, it's sort of, you wind up with the same 1. It's up to you how you interpret it. That's why it becomes a little bit weird and a little bit confusing. So, since we have time, and I think this will make more sense, should we take a 5-minute break and then do a quick introduction to what we would talk about tomorrow? And this way we'll wind up, I think it makes more sense to kind of have a whole bunch of extra time. Well, I'll raise this as if we get into tomorrow's lecture today, we'll have more time to really experiment and get into it hands-on tomorrow at the end of class, as opposed to just saying today, all right, well, let's end earlier and you've got half an hour to, desperately run off and get your lunch or something. By show of hands, does anyone have a preference? Can we keep up? Nobody's too stressed out? All right, we'll go for it. We'll go for it, since the lecture notes are already up there. We'll jump right in. Because the more I try to show this in the sandbox, this part hopefully helps to open up the sandbox a little bit more. Some of this, the caveat here, or the warning, is that some of the sample code is based on the original text that we used to use, but it's similar enough that we can kind of go back and forth. We should be able to go back and forth. Concepts are obviously the same. And it's good to try out things in different ways. So let's do that. All right. Good. I know people are following along online, at least, hopefully, because more people are looking at this project suddenly. Is everyone online still okay? Can I get an okay from everybody? Okay, great. Thanks. All right, so OpenGL. Some of this is a sort of review of last time a little bit, or quick, real introduction to the pipeline notion. But let's talk about how the math portion, the math pipeline meets the OpenGL pipeline, and so on. So nuts and bolts, pipelining your math. Buffers, uniform variables, and shaders. We didn't mention uniform variables last time. We talked about buffers, we talked about shaders. Buffers contain most of our data. Shaders is how we kind of finalize that data, get it to be on the screen, get it to be transformed, and so on, potentially. But what are these uniform variables? They become important as we start talking about our transformations and so on, because sometimes we want to do things like talk between the actual C++ code, the CPU code, and the GPU code to tell it about these things. Oh no, what is that? Is that just Outlook? The VPN failed to connect? I suppose I don't need the VPN right now, do I? All right. So, fundamental OpenGL thing. A lot of the time the question is, okay, how do we get data between the CPU, between our running program on the CPU, on our Ryzen or our Intel, whatever it is, that processor, and the GPU, the card over there, right? There's two main methods that we use to get stuff in between our different types of processing units there, our graphics processor and our central processor. The one we talked about last time was more about this buffers containing vertex attributes, which might have been the coordinate of a vertex, or might have been the color, it might have been a UV. We didn't talk too much about the UVs. But they were something that was unique to every vertex. It had some attributes, something about it. Like I said, the coordinate, this vertex is here. The color, this vertex has this color. Right? So every model, every vertex in the model, you have this notion of indexes, but every vertex in the model has unique characteristics to it. It may be shared by multiple polygons, but it has its unique things. They tend to be a lot of them, right? Lots of polygons, lots of vertices. Usually these large arrays of them, or large vectors of them, if you're kind of creating things in your CPU side using C++. Or And we send those as buffers, as VBOs, over to the GPU, right? We say, okay, here's a VBO. We define it. We tell it what the attributes look like, how they're laid out. We say, here's the buffer. Go blast it over there somehow. Or this other type is called this uniform variable, right? This is the other means of kind of talking to a shader through these uniform variables. And uniform variables are generally a lot smaller, a lot more precise, a lot more dynamic, actually. So let's quick review. OpenGL, the buffer is called a VBO. VBO is declared and instantiated in the C++ side in your OpenG application. Is that? I was worried it's ringing, right? So what is this other thing, this uniform variable? How did we get it? What's it for? Why does it exist? Don't we cover everything by our vertex buffers? Isn't that everything already? Now, uniform variables are a special case or a special thing that are for values that are generally constant across an entire model that's being drawn. So when we talked about things like our MV, our P, or our MVP, these transformations where we're generally using a single transformation across a whole model, because we want to move that model in space or rotate it around somewhere, we know there's just one transformation matrix that we're going to use across that whole model. But every one of those vertices needs to be transformed by that matrix. So we have this one-to-many sort of relationship, right? One transformation, many vertices that we want to process, which sort of lends ourselves to this massively parallel thing, right? The position of one vertex doesn't really care about the position of the other vertex, how it was transformed. They can sort of be independent, so they lend themselves well to this kind of parallel processing. So the uniform variables are the means for sending values to the GPU that is generally constant for the entire model being drawn, such as maybe one of these transformation matrices. Whereas, recalling what we talked about for vertex attributes, a vertex attribute is really data for each individual vertex. Plus, if you want the variables to be, this is the bonus piece of it, and we'll talk about what this means, but it is a different thing a little bit, that vertex attributes will be interpolated by the rasterizer. Right? This is one of the kind of odd things about the name. You might say, well, what does uniform mean? Why are these kind of large-scale, big things? Why are they called uniforms? Because they don't actually change across the model. But vertex attributes, they are, even though we set them once for the model, as we render them, they actually wind up being interpolated, so they are potentially dynamically changing for every fragment on the screen, not just every vertex on the screen. Right? So they're even more diverse than just the VBOs even. Right? So those attributes, we have the ones that we sent, but then they are even interpolated further and they become even more diverse and potentially a larger data set to deal with. But the uniforms are fixed, right? So when we're going to do things like simple with that, it's going to be much simpler to deal with. Right? So here's sort of, hopefully in a nutshell, kind of how this is working. So on the OpenGL side, we have the VBO, our vertex buffer object, which is sending our vertices somehow, sometimes in combination with an index and so on. Right? Thankfully, the pipeline will stitch together or pull the vertex as it goes to the index list. Will pull the vertex that it needs to and give that to a vertex shader. So the vertices and their attributes come through the vertex shader, but on the side, we sort of have the uniforms, where you're saying, okay, here's the transformation for all of these vertices. Right, so our OpenGL application, our C++ application is going to provide both of those. And then here's where we sort of are done handing off vertices or vertex attributes once the pipeline kicks in. Right? So it's interpolating, creating more of them, more things are traveling through the pipeline, but these uniforms are still available throughout. Right? So we can communicate with various parts of the pipeline using the uniforms, but the vertices, once we kind of push them in the pipeline to begin with, they're sort of like, okay, here they go. You know, we've poured them in, and they're going to keep going through there. Whereas the uniforms are going to allow us to change the parameters for the model. Now, included in here is sort of a sample application, sort of pseudocode, and we'll sort of break it down. Like I said, this stuff is based on the last model. If we encounter any major differences, we'll backtrack and make sure things work. But the biggest difference here is we're going to use GL draw arrays as opposed to elements. So this one, the example here isn't using indices, it's just using a set of vertices. So done once, as part of some initialization phase, we create a VBO, contains the vertices, attributes, data, gets copied into that buffer. So it's typical architecture of an OpenGL program. You set up the VBOs, do that once during some sort of initialization. Then, every time the frame is redrawn, typically in some kind of update loop, perhaps, we want to do things like maybe change the orientation of the model, or move the camera, or move the model, that sort of thing. So, procedurally, we enable the buffer, we associate the buffer with the vertex attribute, we enable the attribute, we draw. That's the simple way that isn't involving uniforms just yet. So we're not passing, in this simple case, vertex attributes, nothing is changing, we're just enabling them and saying, do it, enable, do it, enable, do it. Right. This is that same piece. And every time the shader is called, it gets a new vertex, right? So the top part is what's going on the CPU side. It created a vertex array, created vertex buffers. Now over on the shader side, how does it know about those buffers? How does it know what's where? If we look at a shader code, you'll see this layout which says, oh, okay. And you'll see over here at the top there, layout location 0, layout location 1, layout location 2. That's how the shader knows, right? So we have the CPU saying, okay, bind this VBO, this is the number of that attribute, right? That's how it specifies it. And then over on the shader side, it has the layout there. So whenever you see layout, that's vertex attributes that you're dealing with. Right? So we have position, color, and texture coordinates on this side. Oh, it just jumped all the way back there. All right. It's both on the C++ side here. We've bound a buffer. We put data in the buffer, and then we told it the layout of the attributes in there of buffer item 0, that it is made of 3 floats, it's not inverted, and this is just using a single buffer in this case, a single attribute, just the coordinates, just the positions here. I'm going to wind up like squirting myself with hand sanitizer. Really terrible. Okay. Now, that's easy enough. Set it all up, we just spin in a loop, nothing changes. What if we want something to change? So, on the GPU side, in the vertex and fragment shaders or other shaders that we wind up using, we declare the name and type of the uniform. So this is sort of, kind of think of this a little, I guess I usually think of this sort of opposite of the way that the vertex attributes. I think the vertex attributes is sort of like really beginning life on the CPU side. Whereas I think of the uniforms as beginning life on the GPU side, right? Because there's very little definition over on the CPU side. Maybe. I'll come back to that. So you declare them and name them, and declare the name and type of the uniform on the GPU side. And on the CPU side, you typically are obtaining a reference to a uniform variable and then sending it to that. So there's not really any setup on the CPU side when it comes to uniforms, which again we'll look at here. All right. So you'll see right here I have a uniform matrix for transform up there, and uniform matrix for transform 2. So I've declared two 4x4 matrices that are going to be transformation matrices. And in here, I'm actually using transform 2, and I'm using that to transform all of the points in my model. Now, let's use transform, just transform, because that'll help illustrate. So you see now I said, okay, use the other one. And it's now offset, and it's spinning, rotating. Now, nowhere in this code is there a rotation other than the actual math. I mean, yes, this transformation is performing the actual mathematical rotation, but it's not changing over the course of time. It's just a rotation. So the question becomes, why is this animating? Now, the rotation certainly isn't changing on every vertex. They're actually all using the same rotation. They're using the same transformation on all the vertices. So it wouldn't make sense to recalculate that for every vertex. It would make sense to do just one for the model, because I'm just going to rotate the model. So that's why it makes sense to do this over on the CPU side. So we declared it, we used it over on the GPU in the shader, but on the CPU side, typically in the update loop, I obtain a reference to that uniform variable and then send data to it. So that looks like this. So it has to be already set up in the GPU, in the shader. It has to know about this thing. And it's like in this case, it's created over there, uniform matrix for MV matrix. Then over on the C++, on the CPU side, I can ask, give me the location of it by asking, GL get uniform location. I ask it, I tell it, okay, which shader program are you talking about, and what is the name of it? So it's a remnant of the fact that it compiled it. That's how it knows where it all is. And then, once we have a location, we have a set of functions, and there's a whole slew of these GL uniform matrix for FV. So in this case, we needed to know that it was a matrix 4 of float values, and we're sending it what was a GLM curated matrix, we'll call it. So this GLM value pointer basically converts it from the typical GLM format and make sure that it is shader friendly, just in its matrix 4, right? It says, okay, that contains the data to be sent. Generally, we create that, we let GLM curate it. It keeps it doing the right thing. So in our sample, let's see what that looked like. And then maybe we'll stop there. So in main, if we look in the main program here, and now I'm forgetting if I added this before or after putting it in GitHub. We'll make sure. But in our main loop, right, here's our main function here. We set up GLFW, and so on and so on. We set up the actual textured quad we wanted to use. That's where we sent the VBOs and did all that kind of setup. And here's basically our update loop, right? While no signal for the window to close, that's what's drawing on the screen. And the important part for the spinning is this right here. So you see right here, it has two matrices declared as transform and transform 2. They could be anything. They don't have to match the names of the ones over on the shader side. That's not what's important to match over there, that transform and transform 2. But they're just going to be matrices. One of them starts off to be just a identity matrix. The other one is a matrix that is the one that's set in the GUI there. Right, so in one case, I have a GUI that is explicitly setting what that matrix is. The other one, I just start off with an identity. And you'll notice there's two things here. This basic transform it does a translate, which is move it over 5 and down, or over by 0.5 and down by 0.5, right? And then rotates it this is the vector that it's going to rotate it by, which is basically z, which is the thing pointing out of the screen, which is why it's just rotating it in the world there, right? Because it's rotating around its z-axis there. And you'll see that for the angle, it's using GLFW get time. So the angle is being set according to the time that the program is running. So we have this new transform matrix, which is a translation and a rotation. And the actual part where we tell the shaders about it is this line right here, where we're using GL uniform matrix 4FV to say, all right, here's the shader, here's the location, get the location by asking GL about it. I say, okay, by the way, I'm interested in the shader, or the uniform called transform from our shader, and I pass it that value. Let me increase the transform and transform 2. One is in transform and one is in transform 2. So then every time draw elements gets called, or draw arrays, or whichever is doing your actual rendering now, that uniform variable has been updated, so the next time it goes to draw it, it now knows about that new rotation. So that's how that works. Any questions on that? Were you following along the code? Did it have the transforms in? Did it have the uniform variables in the version? Nobody's following along? Everybody's checking other stuff? All right. It would be in main.cpp. Just look for GL program uniform. Is there any GL program uniform lines in there? Yeah, I might not have put that in there.
Yeah. I only have basics and simple. Everything else is...
Oh, okay, that one should be, all right. What you need to do is go, if you're looking at the sandbox, you're going to need to do this. By default, you can't have two mains in your program, right? Can't do that. That's no good. That's general C++ issue. So what happens after it builds the project is it includes, in your source files, it will say, you'll see simple.cpp in there, right? Now, before you change anything, go to the directory that it is in, and is that the one it's in, or? Why am I drawing a blank on where we are? Nope. Here we go. So in the sandbox, you'll see a source directory, project 1. You may see main.cpp with an underscore after it, right? Do you see that in your sandbox source project 1? Right? Change its name to main.cpp. Just get rid of the underscore. The reason that's there is because we don't want CMake to see that as yet another C++ file to just build into our solution, right? So we can't let that happen. So that's why it kind of isolates it, so it doesn't put it in there automatically. But now, since we're going to be doing the next step by hand, it's okay. So leave that as .cpp, change it to CPP, and now you can go into your Visual Studio project and decide, say, all right, now if I could choose simple.cpp, right-click on that and say remove it. Right? So now I don't have simple, I don't have main in here. So if I compiled here, let's say, no good. It's not gonna be happy. Right? Failed because there is no main in my program now. So I have the choice. Oh, don't run that. I'm then going to go to source files, right-click on source files and say add existing item. And I could choose, let's see, I'm going to go into sandbox, source, project 1, and choose either main.cpp or simple.cpp, whichever one I want to use. So choose main.cpp. You'd have one or the other in your project. And then you can run that one or check for that one. That should be there, right? So if you want to check if there's any uniforms in there, otherwise refer back to today's lecture and see how you might add that. Right. So again, the combination, if we went through today, and yeah, this week is really kind of jammed all into one thing. What we've effectively done for this week, you'll see that there's shaders. We're going to basically sort of cover everything in getting started. We should be all done getting started, except for textures by the end of this week. So if you want to refer to that, and even in shaders, if you look at these shaders with the sandbox in mind, you'll see there's some examples about different uniforms that it uses and so on and so on. Right? Like I said, so just about anything you do on this site, you should be able to easily, and if you can't, let me know, to easily implement using the sandbox if you want to kind of see it live. The cool advantage in ours is that you can dynamically change stuff in the shader, and we're going to incorporate IMGUI so you can really kind of play with it as it's going on. So we'll end today there. can sign off to everybody on Discord, and if anyone does have any questions, you can always ask me in person or send them on Discord, and we'll try to get those dealt with that way. All right, see everyone tomorrow. I'm signing on to Discord. I'll be in person a little bit here for a while.